Questions about anything? Well, today's the day I'm going to demonstrate the Cauchy-Riemann equations. So this is the first time that we're going to see something in complex calculus that seems different than real calculus. It's different and new. So to help us understand this, I'll need a simple lemma here. We'll always today be writing f complex function u, so it's a function of complex number x plus iy, and it spits out a new complex number. And I'll call the real part of that thing u of xy, and the imaginary part v of xy. And sometimes I'll use z instead of x and y, and it'll be z is x plus iy, and we'll be differentiating at a point, and so z naught will be x naught plus I y naught. I'll be writing that all day today. And so the little lemma I need is that a complex limit exists Let's see, so that limit is going to be a complex number. Let's say it's a plus ib. Let's call that complex number L for limit. Okay, this complex limit exists if and only if the two limits in R2, so that would be the limit as xy tends to x naught y naught, of u of xy equals a. And let's see, I can be lazy here. Let me copy that. And the same thing about the v is equal to the other component, b. Okay, that's a very simple thing to understand. I'll draw a picture so you understand it. The y here is, let's see, so let's put a plus bi over here, and let's put f of z over here. Then this distance would be the distance f of z minus L. And this distance here of a right triangle would be v of xy minus b. And this distance here would be, the length would be u of xy minus a. And so the demonstration of this fact would be, let's see, it's simple. We see the lemma from, let's say if the limit is L, then the limits on the other side would be dominated by the hypotenuse. So this direction is due to the fact that legs of a right triangle are less than or equal to the hypotenuse. Okay, and the other direction is the Pythagorean theorem. Because if both those legs go to 0, then the hypotenuse goes to 0. So that's all there is to that. Questions about that? Well, now I'm going to demonstrate the Cauchy-Riemann equations. And there's two directions that are going to be of interest to us. Let's see, I guess the Cauchy-Riemann equations have to do when something has a complex derivative And let's see, I told you what they are. I'll use the standard notation for partial derivatives. Du dx equals dv dy, and du dy equals minus dv dx. Those are the Cauchy-Riemann equations. And so, let's see, for the first one, to understand where they come from, let's suppose, here's the step one in understanding these things. Let's suppose f is complex differentiable at just one point. Remember, to be analytic, it's got to be complex differentiable on an open set. But right now, we're just going to suppose that f of z is complex differentiable at a point z naught. And now the Cauchy-Riemann equations are derived by calculating this derivative in two ways. One way is to slide in from the horizontal. So let's suppose this is x naught plus I y naught here. And let's see, if I slide in from the horizontal, this point here would also have the I y naught coordinate, but this would be an x plus I y naught. Okay, and I'm going to slide into the z naught point along this horizontal line. I know that that limit has to be the same as the derivative. So the difference quotient, let's calculate it. That's f of z minus f of z naught over z minus z naught. And that's equal to let's see, that f of z over there is x y naught. And then we said, let's see, plus I, same thing for v of x y naught, minus this, the same thing at the base point. And now on the bottom, z is x plus I y naught, and z naught is x naught plus I y naught. Notice that the I y naughts cancel in the denominator. And so I get something pretty simple here when I split it into real and imaginary parts. I get u of x y naught minus u of x naught y naught over x minus x naught plus I times the same kind of difference quotient, which you recognize is the difference quotient for a partial derivative. So we discovered something here that Cauchy would have discovered. That difference quotient, if it goes to a limit, if dq goes to f prime of z naught, then the lemma, then the real and imaginary parts, lemma shows that the real and imaginary parts go to, let's see, the lemma shows that real and imaginary parts have limits. And so we conclude that the first partials exist. So the first partials x and y, let's see, x, those first partials in x exist. That's important, step one. And I'm going to call this red box number 1. That's not in the book, but I'll refer to this as red box number 1 for the rest of the course. So f prime of z naught equals du dx at x naught y naught plus I times dv dx. This is kind of the easy direction. Okay, I'm going to call this red box number 1. I'm going to get a red box number 2. It's going to look different, and that's going to give us the Cauchy-Riemann equations. Red box number 1. It's the easiest of the 2 red boxes to remember. Okay, the next case now is to do it vertically. So let's see, when I do it vertically, I still got my base point, which is x naught plus I y naught. But now when I want to slide in from a vertical direction, let's see, the x naught would be the same, and the y would be sliding. Okay, we do the same routine again. I'll try to speed it up this time. The difference quotient for the derivative, let's see, that would be f of x naught plus iy minus f of x naught plus iy naught. And let's see that on the bottom now. Notice that this time it's the x naught that cancels in the bottom. Okay, and when you play, I'll speed it up this time. When you play the game, you'll get here u of x naught y minus u of x naught y naught. But in the denominator, I get I times y minus y naught. So that's something totally different than the other side. And notice in the next one, the i's are going to cancel, and I'll get v of x naught y minus v of x naught y naught divided by y minus y naught. And now as I slide in and let the limits go, let's see, I'll use the fact that this is a real thing. And so it's going to tend to, notice that it's going to tend to dv dx, no, dv dy, dv dy at x naught y naught. That's the real part of that thing. And notice that 1 over I is equal to minus I. So this part is going to go to minus I. Put the big fat minus sign here. And that one is the partial derivative du dy at x naught y naught. And similar to previous considerations, that so this tends to that. We conclude that those first partials in y exist. So the first partials in y exist. Last one, it was x, so this is the y ones. So it's important to know they exist, and not only that, but they slide into the derivative. And so you get red box number 2, f prime of z naught is equal to dv dy at x naught y naught minus I du dy. and that's red box number 2. The Cauchy-Riemann equations come from equating those 2 red boxes. The real parts would give me the first equation, and the imaginary parts give me the second equation. So last step, equate the red boxes. To get the Cauchy-Riemann equations. That's all there is to it. So I guess I should call this a theorem. Theorem. If f equals u plus iv is c differentiable at z naught, then the first partials of u and v exist at z naught. Of u and v. I guess instead of saying z naught, I should say at x naught, y naught. And the Cauchy-Riemann equations hold. Actually, I like to state the Cauchy-Riemann equations in the form of red box number 1 and red box number 2. So f prime of z naught is equal to du dx plus I dv dx, and it's equal to dv dy minus I du dy at x naught, y naught. Those are the Cauchy-Riemann equations. Well, the Cauchy-Riemann equations are what you get when you equate real and imaginary parts. Yeah.
What do you mean the first partials of u and exist?
I mean and v. Thanks. I do stuff like that frequently. Questions about that? So let's see. Last time I had to do some work to see that the complex conjugate is not complex differentiable. Let's see. F of z equals z bar. That would be x minus iy. So in this case, the u of xy is just x. And the v of xy is minus y. And if I were to check the Cauchy-Riemann equations, let's see, the du dx would be equal to 1. And the big question is that equal to dv dy, which is minus 1? And so that's a big fat no. So the first Cauchy-Riemann equation fails. The second Cauchy-Riemann equation would be du dy. That would be 0. And let's see, this other Cauchy-Riemann equation would be equals minus dv dx. Minus dvx is also 0. That's a yes, but who cares? If one of them fails, that's all that matters. Yes. But who cares? Okay, so what I'm using here is the fact that if the thing is complex differentiable, then both the Cauchy-Riemann equations hold. So f prime exists implies both Cauchy-Riemann equations hold. They don't. They don't both hold. So f is not complex differentiable. So z bar is not C differentiable. So that's one use of the Cauchy-Riemann equations. It gives you an easy test. Let's do another example. E to the z, e to the x plus y, we know is, after playing games, we defined it as e to the x cosine y plus I e to the x sine y. And here that gives us, this is the u, and this is the v. And it's very simple to check that both Cauchy-Riemann equations hold. And so the big question, does that mean that e to the z is C differentiable? Well, the answer is going to be yes, of course. Okay, so we showed that the Cauchy-Riemann equations, now what did we show? We showed f prime exists, implies the Cauchy-Riemann equations hold. The big question, is the reverse true? And the answer is yes, of course, but with some minimal assumptions. That I'll describe right now. Assumptions about the minimal further assumptions about the u and the v. And that those are, u and v need to be C1 smooth. I'll say what I mean by C1 smooth in a second. There's weaker versions of this thing. There's a famous thing called the Luhmann-Menshoff theorem, but it's a lot of extra work. And so this is the minimal assumptions we need to make it sort of straightforward and easy. And it's also traditional. And in fact, many books add this to the definition of complex differentiable, just so they can avoid anything subtle about this. Questions about anything? So the theorem is going to be, if u and v are C1 smooth on an open set. You need an open set for this. I didn't need that when I derived the Cauchy-Riemann equations. I just needed differentiability at one point. If u and v are C1 smooth on an open set, omega, and I guess I should say that means that u and v are continuous, on omega. The first partials exist. That's where the 1 comes from, first partials of both of them exist and are also continuous. In homework 2, you'll notice I used the word C2 smooth. That's the same thing, except the first and second partials all exist and are continuous on omega. Okay, to continue, and let's suppose that u and v satisfy the Cauchy-Riemann equations. Then then f, which is given by u plus iv, is analytic. That's a fancy word, remember. It's analytic on omega. Which means that it's complex differentiable on that open set. So it's critical that when you talk about analytic, that you're talking about an open set. Okay, to get rolling on this, I'll need an elementary calculus lemma about first-order Taylor theorem in 2 variables. You probably saw it somewhere, like Math 261. I'll give you a demonstration of this that's rigorous in case you haven't seen it someplace later. But if u of xy is C1 smooth, near x naught, y naught, then we can approximate the function u very closely by its first-order Taylor polynomial, which is u of x naught, y naught, that's the constant term, plus du dx at x naught, y naught, times x minus x naught, plus du dy at x naught, y naught, times y minus y naught. Let me move this over so I can fit something in here. Then, let's see what's here. This would be a remainder term. So I'm approximating u by its first-order Taylor polynomial plus a remainder. This is the first-order Taylor polynomial. And that's the remainder. And there was a higher-order Taylor's theorem that you learned in multivariable calculus, where there was very special forms of the remainder. And in fact, this fact comes from looking at those and simplifying the proof for the first order case. So I can get a relatively simple demonstration of this, where so that if it's C1 smooth, the first order Taylor approximation is good. And so it goes to 0 very rapidly. The difference between u and its first order Taylor polynomial goes to 0 so rapidly, in fact, that if I were to look at that remainder, let's see, of course the remainder goes to 0. That's not hard to see. That's basically just continuity. So the remainder goes to 0. But it goes to 0 so rapidly that even when I divide by something that goes to 0, like the distance between the 2 points, xy and x naught, y naught, even if I divide by something that goes to 0, it still goes to 0. So that's fast, swift going to 0. Well, I'm going to assume this calculus lemma for the moment and demonstrate the theorem. So we assume the lemma for now. And now I can give you the proof of the theorem. And so I don't have to write all those stupid subscripts, x naught, y naught, over and over again. I'm going to do some notation here. Let's see. I'll write u sub 0, it's super 0. U super 0 is u of x naught, y naught. And I'll write du dx super 0 is shorthand notation for du dx at x naught, y naught, etc. Same thing for all of these. Then I can simplify my notation. My difference quotient then would be f of z minus f of z naught over z minus z naught. That would be u plus iv minus u naught plus iv naught over z minus z naught. Okay, now you think of that formula in the calculus lemma above there. I've got a u minus u naught. Let's go back and look at it. I can take that u of x naught, y naught on the right-hand side of the big hairy formula and put it on the other side. That would give me u minus u of x naught, y naught. And that's equal to the first order Taylor polynomial plus the remainder. Okay, so now I'm going to use that fact right here. That's equal to the first order Taylor polynomial, du dx naught times x minus x naught minus, plus du dy naught x minus x naught, y minus y naught. Okay, and then I'll call this remainder over here that I'm not even, the next part, ru. I'm going to divide this thing by z minus z naught. Okay, that's the real part. This is going to be a plus ru also by z minus, dividing by z minus z naught. Okay, and now I get the same thing, but now I'll have imaginary part. Same thing for the v's. And so that'll be the first order Taylor approximation of the v's. Times x minus x naught plus vy naught times y minus y naught. Okay, and the remainder part for the v1, I'll call that r sub v. Okay, this looks like, oh God, this is a mess. But now I'm going to use the Cauchy-Riemann equations. Let's see. And I like red box number 1 the best. It's my favorite red box. And red box number 1 only has derivatives with respect to x. So I'm going to use the Cauchy-Riemann equations to get rid of the derivatives with respect to y here. So du dy is equal to minus dv dx naught. And here's another one I hate. That dv by dy is du dx. So that purple stuff is the Cauchy-Riemann equations. And I was selective in trying to get rid of the y derivatives. And now a miracle happens. That is complex multiplication in the numerator. We see complex multiplication. In the numerator. Okay, and so in fact, that mess on the top there is red box number 1. Du dx naught plus I dv dx naught. And let's see, times x minus x naught plus I times y minus y naught. And we're dividing that mess by z minus z naught. Okay, that's red box number 1. And of course we have the remainder. So I'll call this remainder script r over z minus z naught. Well, that thing, x minus x naught plus I, y minus y naught, that's equal to z minus z naught. So those are going to cancel, and that's the wonderful thing. So that difference quotient I now have written as red box number 1 plus the remainder. I guess I want to call this just plain old remainder. And of course that remainder is going to go to 0 fast, or fast enough. So where the modulus of the remainder is less, let's see, that would be equal to the modulus of Ru plus I Rv over z minus z naught. That's less than or equal to Ru over that square root of that big mess, that's the distance there, plus Rv over the distance from z to z naught is the square root stuff in the denominator. And our calculus lemma says that goes to 0. As zw tends to zw naught, z naught x, sorry, you know what I mean. And we're done. So that shows that f prime exists and is equal to red box number 1. And once you know that, you get the Cauchy-Riemann. We know we're assuming a Cauchy-Riemann equation, so I don't have to show red box number 2. I know it already. If I had gotten rid of the x derivatives instead of the y derivatives, I would have had red box number 2 there. So we're done. That's the end of the proof. Assuming the calculus lemma. Okay, so a simple corollary is e to the z is analytic on the whole complex plane. And when I do red box number 1, d by dz of e to the z is itself. Let's check. That's an easy thing to check. D by dz of e to the z is red box number 1. And that's equal to d by dx of the u function. That's e to the x cosine y plus I d by dx of e to the x sine y. Of course, derivative of e to the x is itself. So sure enough, that's the complex exponential. Check. I could have used red box number 2 and get the same thing. Let's see. I guess it's time for some remarks. I don't want to get too involved in... I don't want to prove that calculus limit today. I'm going to save it for next time. Give it a quick proof. Just more about the philosophy of what the Cauchy-Riemann equations mean. So, remark. When we're thinking of our mappings, mapping R2 to R2, then we have xy goes to u of xy, v of xy. And you might remember from multivariable calculus, there was something important called the Jacobian matrix. J, you take the gradient of the first function and put it in the first row, and then you take the gradient of the second function and put it in the second row. And when you think about what the Cauchy-Riemann equations mean, that's equal to, let's see, du dx, I'll call that A. Du dx is equal to dv dy. And du dy, let's call that B, is equal to minus dv dx. So that would be, make this a minus B. So it means when the Cauchy-Riemann equations hold, this Jacobian has a special form. And of course, the Jacobian matrix represents a linear function from R2 to R2. So the Jacobian matrix maps R2. When you use it, think of it as a matrix for a linear transformation, then it gives you a linear transformation from R2 to R2. And the Cauchy-Riemann equations mean that this is exactly representing complex multiplication. Okay. The Cauchy-Riemann equations implies that this linear transformation represents complex multiplication. And when you think about it, what does it mean? That difference quotient means that locally the function looks like a complex linear function. The next thing we want to think about, let's think about it a little bit today, is doing the Cauchy-Riemann equations twice. Well, it's not, you might say, well, why would I think about something that probably is not going to be true? So, it's easy to come up with real functions that are once differentiable, but not twice differentiable. If I asked you to try to think of a complex function that was once complex differentiable, but not twice complex differentiable, you would never find one. There's no such thing. So a miracle, I'll call this an amazing fact that allows us to, that makes this a worthwhile thing to think about. If F is analytic, meaning complex differentiable on an open set, then so is its derivative. Exclamation point. That's a very special thing about complex differentiable functions. Nothing like it is true in real variables. So this thing is way false. R to R. But a remarkable fact in the complex case, and of course you can do it again and again. So the amazing thing is that if F is analytic, implies F prime is analytic, implies F double prime is analytic, etc., etc. Dot, dot, dot. And when you think about it, remember, F being analytic meant that U's and V's had first partial derivatives, etc. And if you do that again, it means they have second partial derivatives, etc., 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 etc. We conclude that the U and the V are actually C infinity smooth. So we're able to conclude that U and V are infinitely differentiable, and all those derivatives are continuous. So that's called C infinity smooth. All partial derivatives exist and are continuous. And more than that, we are able to conclude that U and V are harmonic functions. Those are pretty special functions that come up in all over the place in science and engineering functions, meaning that Laplacian of U is equal to 0, and Laplacian of V is equal to 0. And you remember what Laplacian means? It's d2u dx squared. That's a second order partial differential equation. d2u dy squared equals 0. That's the Laplacian. And in fact, harmonic functions are going to have a very close relationship. We call it an intimate relationship with analytic functions. If you have a harmonic function, you can always find a v so that u plus iv is analytic. And conversely, the real and imaginary parts of analytic functions